Hello, welcome to today's class. I'm glad to have you here. Today, I want us to look at the concept of current electricity. Now, we can look at current from two angles, which is a charge. Now, charges could be at rest or it could be in motion. But before we start, please, if you have not subscribed to this channel, please hit the subscribe button, hit the like button, and then share this video with your friends. Now let us go. Now we said for current, charges can be at rest or in motion. So when charge is at rest, we call it static electricity. But when these charges are in motion, we call it current electricity. Now, electric current or electricity is nothing but the flow of charge or flow of electrons. So those flow of electrons or flow of charge is as a result of electrons in motion, or as a result of motion of electrons. Now this motion of electrons are caused by electromotive force. So those electromotive forces push current to start to flow, or push electrons to start to flow. So when these electrons are in motion, we say we have current electricity. Now this the flow of current most times is different from the flow of electricity. Now let us look at it. Now assuming we have a circuit like this, this is the positive terminal, and then we can have this as our negative terminal. Now this terminal can have a key here, and then we have this. Let's say we have a resistor here. Now if we have a resistor there, now we can have, let's say, a bulb. This bulb is represented by X, which is a load. Now we can have this. So this is the key. Now this is the electromotive force. Now this is the bulb. Now while this is our resistor. Now in this case, now if we have conventional current flow can move from, this is a conventional current flow. Conventional current flow. Now if it flows from positive to negative, we have conventional current flow. Now if it flows from negative to positive, it will give us electron flow. So this is the flow of electron flow. And of course, if an electric circuit is discharging current, it will now flow from positive to negative. Now if you want to recharge that electric circuit, you pass current backwards. So if you pass current backwards, that is the flow of electron, you will get it charged. Now we talk of the production of electricity. Now there are so many ways that electricity or electric current can be produced. For example, we can have the use of solar cells, or from the solar panel. We are told that here is that electricity, once light of appropriate frequency shines on a metal surface, electrons are knocked off. And once electrons are knocked off, then electricity is generated from that source. Now we can also have the use of accumulators, of course car batteries, or used from a simple cell. So electricity can also be generated from that. Of course we can refer them as chemical energy or chemical process. So that is, in that case, electricity can be generated. Electricity can also be generated from generators, of course the dynamo, or through electromagnetic induction, or we call it induction coils. So through that process we can generate electricity. Okay, so and of course we are used to the gen set. So electricity produced from the gen set or dynamo is also a process of producing electricity. We can also have electricity produced from windmills. We can have electricity produced from tidal winds. We can have electricity produced in that process. We can also have electricity produced from thermal process or geothermal process. Electricity can be generated in that process. Of course, thermal, you know what thermal process means, through heating. So electricity can be generated by that process. We can have electricity generated from gas turbines. From gas turbines, we can have electricity generated in that process. Now, it is worthy of note that yes, since we have, this is a complete circuit, circuit consisting of your key, which is a switch, the source of electricity, or we can have the battery here, we can have the resistor here, and then we can have an additional load. This one also is a load, but this bulb is an additional load. So in other words, we can have this. Now, it is worthy of note that for current to flow, there must be a complete circuit. If this key is open, current cannot flow. So the moment we close this key, current flows. Okay. Now, we'll look at potential difference. Most often, questions come from either potential difference or electromotive force, and students tend to mistake potential difference for electromotive force, please. Electromotive force. Now we take the two. The first one is potential difference. Now potential difference is nothing but the work done in moving an electricity or a moving electric charge of 1 coulomb from one point to another. Or you can say that yes, it is the work done in moving an electric charge of 1 coulomb round a complete circuit, because the moment it moves from this point to another, it has moved round. So it is the work done in moving a charge of 1 coulomb from one point to another in an electric field. And of course, potential difference is measured in volts. It is measured in volts. Okay. Now we talk of electromotive force. Electromotive force. EMF. Most time we'll call it EMF. Now electromotive force is nothing but the terminal PD. PD across the terminals. So we say terminal PD across the ends of a cell when that cell is not supplying current to an external circuit. So when that cell is not supplying current, what you have there is electromotive force. But when it is supplying current, that is when it is moving current from one point to another, what we have is a potential difference. Potential difference. So we take it again that yes, for electromotive force, we say it is the terminal PD across the ends of a cell when that cell is not supplying current to an external circuit. While for potential difference, it is the work done or energy released per coulomb when electricity moves from one point to another, or when that electricity is supplying current to an external circuit. This one is supplying current to an external circuit. This one is not supplying current to an external circuit. Of course, the two of them are measured in volts. Okay. Now, let us look at Ohm's law. Ohm's law says that current passing through a metallic conductor is directly proportional to the PD across its terminal, provided that temperature and other physical factors are kept constant. Or we can say that yes, Ohm's law states that current passing through a metallic conductor, example wire, of course wire is an example of a metallic conductor. So current passing through a metallic conductor, example, wire, is directly proportional to PD across the terminals of that wire, provided that temperature and other physical factors are kept constant. So in other words, we can have that current passing through a metallic conductor, we say it is directly proportional to the PD across the terminals, provided that temperature and other physical factors are kept constant. So we say that PD across the terminal is directly proportional to the current there. Of course, we know that if we remove this sign of proportionality, we introduce a constant. V is equal to IR. Now, where V is the potential difference, I is the current. Of course, potential difference is in V, current is in ampere. Now, the other one is R. R is the resistance in ohm. Now, this resistance, from here we can say that R is equal to V all over I. We can put this in box. Now, at this point, we can now define resistance. And we can say that resistance is nothing but the opposition to the flow of current in an electric circuit. So the opposition to the flow of current in an electric circuit. Now, remember we said earlier that provided that temperature and other physical factors are kept constant, that this law holds. Let us look at those factors that should be kept constant, because if you don't keep those factors constant, it will affect the resistance. Now, that will take us to factors affecting the resistance of a wire. Now, factors affecting the resistance of a wire include the following. One, we have said that length of wire, L. Now, we say that the length of wire, how does it affect R? We can say that R is directly proportional to L. So in other words, the longer the wire, the higher the resistance. Or the shorter the wire, the lesser the resistance. Therefore, if you are performing any electrical connection, be careful, be mindful of the length of the wire, because the longer that the wire, the higher the resistance, and vice versa. Now, the second factor that we need to keep constant if we are performing that experiment is the number 2, area of wire. Area of wire, A. Now, the resistance of a wire is inversely proportional to the area of a wire. Now, this area, of course, we know what inverse proportionality means. It means that the thicker the wire, the lesser the resistance. While the thinner the wire, the higher is resistance. Okay, we have said these two. Now, the third one, of course, we have mentioned it, is the temperature. And we say that yes, R is directly proportional to the absolute temperature. So in other words, the higher the temperature, the higher the resistance. So the lower the temperature, the lesser is resistance. So these three factors must be kept constant. As usually, it is not advised to use longer wire, because the higher the wire, resistance will be higher. Okay, the longer the wire, please, the resistance will be higher. So in other words, keep the wire short, keep the size of the wire, keep it constant, and then temperature, make sure you work with a lesser temperature, because the lesser the temperature, the lesser the resistance. Now, the last but not the least, nature of wire. Some electrical wires or some wiring materials are made of copper, while some are made of silver and some are made of aluminium. That they are made of copper does not mean that yes, they are the best. Now, for nature of material, we say that the best wiring material is made of silver. It's made of silver, followed by copper, and then aluminium. So each of these, they have their own working principle, but silver is the best, followed by copper and aluminium. So if these factors are kept constant, this law will be obeyed. Now let us look at the resistivity. Now, having looked at resistance, we said it is the opposition to the flow of current in an electric circuit. Now we have resistivity. Resistivity is defined as, or we can say, the resistivity of a material is defined as the resistance of unit length of material or unit length of wire of a unit cross-sectional area. So resistance of a wire of material of unit cross-sectional area. Now we can have the relationship between resistance and the resistivity as R is equal to rho L over A. Now if we have a rho L over A, we can, where R is the resistance, rho is the resistivity, L is the length of wire, and then A is the area of wire. We can cross multiply to get rho. If we have that, we have that rho is equal to RA all over length. So this is it. So that's why we say it is the resistance of a wire of unit cross-sectional area of unit length. That is why we have this. So we can now say if the area of the wire is 1 meter, 1 meter squared, and then length of this wire is 1 meter, what do we have here? It simply means that if this is 1, this is 1. Therefore, 1 times this all over this will now give us that rho automatically become the resistance of that material. Now we can now look at the conductivity. So this is the resistance of the material. Now the conductivity of a material. Now conductivity sigma is equal to the inverse of the resistivity. So the conductivity is the inverse of resistivity. So in other words, we can now have that R is the resistance, L is the length of the wire, A is the area of the wire, then rho is the resistivity, and then finally we can have the conductivity. Have this as a conductivity. Resistance, like we said before, is measured in ohms. Length is measured in meters. Area is measured in meters squared. Resistivity is measured in ohms meter. While this, because it is a inverse, this is inverse of this, it will give us ohm per meter. Now let us take some calculations to add flesh to what we have just discussed. Now let's go. Now we have this question on the board. The question says, calculate the resistivity and conductivity of a wire of length 2 meters and the cross-sectional area 0.05 0.004 cm squared. Now we take it one after the other. The first question says calculate the resistivity rho, and the second question says calculate the conductivity. Now we are given that the length of the wire is 2 meters. Cross-sectional area is 0.004 cm squared. Then resistance is given to be 3 ohms. If we quote the formula given to us, we know that yes, rho is equal to RA all over L. That is the formula. Now we have this area given to us. If you take a closer look at this, area is measured in cm squared, length is measured in meters. There are two things there. It's either you convert the length back to this, to cm, at the end of the day, you return it back, or you convert this to meter squared. Of course, the actual SI unit for area is meter squared. And of course, if you want to convert this, you cannot just divide by 100. Since if you're moving from cm to meter, you divide by 100. In this case, you must take note of this square sign here. If you are moving from, there are two ways of solving it. I will solve one of them. Maybe you solve the other one. I can put this one to cm. So length, I can say let the length be, since it is meter, I can convert it to cm. So it will now be the same SI unit with this one, which will now give me, if you are moving from cm to meter, you divide by 100. Now, if you are moving from meter to cm, you multiply by 100, which will give us what? 200 cm. I think with this now, I can now work it. But if you bring those things here, we'll now have that rho is equal to r. R is 3. You put it here. Multiply by a area. Area, I want to use this 0.004 all over the length. The length, I am using this one now because it is in the same SI unit with this one, 200. So which will give us, if we multiply out, we have 3 times 0.004, it will give us 0.012 all over 200. Now 0.012 over 200 will give me 0.00001234. 4 zeros before 6. Of course, if you convert this to standard form, it will give you 6.0 times 10 raised to power 1, 2, 3, 4, 5 minus 5. Therefore, since we moved back to cm, you must note it. So rho will now give us 6 times 10 raised to power minus 5. Instead of ohms meter now, it will now be ohms cm. At this point, you can convert to meter at this point now. If you want to convert to meter at this point, you divide by 100. And of course, that 100 that you multiplied, you divide it. Divide everything by 100. If you divide everything by 100, it will now give us 6 times 10 raised to power minus 5. Dividing it by 100 means multiplying by 10 raised to power minus 2. The same thing. So which will give us that the resistivity rho is equal to 6 times 10 raised to power minus 5 minus 2 will give us minus 7 ohms meter. So now let me help you. You must get this answer. If you want to get this answer, all you need to do is since area is in, I want to write here, area is in 0.004 cm squared. All you need to do is divide by 100. After that, you square. Divide by 100 square. 100 squared. So then whatever answer you get, it must correspond with this. Now the second question says the conductivity. Of course, we know that conductivity is 1 over rho, inverse of rho, which will give us inverse of this. So inverse of this will now give us 1 over 6 times 10 raised to the power minus 7. It will give us if we take the inverse of this, we'll now get 1.67 times 10 raised to the power positive now, because by this one now, it will now move up. It will move up. Once it moves up, we will now have 1, 2, 3, 4, 5, 6 raised to the power positive 6 ohms per meter now, because I use this. If you use this now, it will be ohms per cm. Okay, now let us take another question. Now we have this question on the board. Calculate the length of a constant time wire of diameter 0.6 millimeter and resistivity 1.1 times 10 raised to the power minus 6 ohm meter. Required to construct a standard resistor of resistance 35 ohms. Now, how do we solve this solution? The first thing we do is bring out the parameters given to us here. The length is what we are looking for. Then the diameter of wire is 0.6 millimeter. Resistivity there, rho, is 1.1 times 10 raised to the power minus 6 ohm meter. Now R there is 35 ohms. Now we quote our formula as usual. With the formula says rho is equal to RA all over L. In this case, we can make L the subject. If we make L the subject, L will give us RA all over rho. Now we have the first thing we're going to do. We have this. What is our area? The area is not there. How do we get the area? In order to get the area of a wire, area of wire is equal to, either you say pi r squared or pi d squared over 4. Please just use, because we are given the diameter here now. So area of a wire is pi d squared all over 4. Pi d squared over 4. But then d, remember d is in millimeter. First, convert it to meter. How do you convert d? We say, but d is 0.6 millimeter. Move it to meters by dividing by 100. So if we divide 0.6 by 100, sorry, by 1,000, please. If you divide by 1,000, you get 0.0006 meters. That is our diameter now. Now, having gotten this, we put it here. Area is equal to pi. Pi is 3.142 multiplied by square of this, 0.0006. When you square it, you divide everything by 4, which will give us 3.142 multiplied by, now square of 0.006 will give us, in fact, I'll put it in standard form. If you put it in standard form, it will give us 3.6 times 10 raised to power 1, 2, 3, 4, 5, 6, 7 times 10 raised to power minus 7 divided by 4. Now area will now give us the whole of this times this divided by 4 will give us everything will give us 2.83 times 10 raised to power minus 7 meters squared. Now this is our area. Having calculated our area in this process, we come here and say L is equal to R. R is 35. 35 times area. 2.83 times 10 raised to the power minus 7. Everything is over the length. Sorry, everything is over the resistivity. Whereby the resistivity is 1.1 times 10 raised to the power minus 6. Now, which will now give us, I'll leave this and take care of this. Now, which will now give us 35 times just 2.38, 2.83. It will give us 99.05. Remember, I will now bring in this one times 10 raised to the power minus 7 all over 1.1 times 10 raised to the power minus 6. I will take care of this base, the basis. I will take care of the basis. If I take care of the basis, 99.05 divided by 1.1. 99.05 divided by 1.1 will give me 90 times 10 raised to power. Now I have minus 7 here. If I send this one up, it becomes plus 6. Therefore, the length, I want to clean up here so that you can pause it. Since we have gotten this, I can clean this. So if we now do that, we have that length is equal to 90 times 10 raised to power. Now this is minus 7. Minus 7 plus 1 will give us minus 1. Now 90 times length to that 90 times 10 raised to power minus 1 is 9.0. Therefore, the length of that wire is 9.0 meters. It is meters because I converted this one to meter. If I had continued to work with this, the answer would have been a millimeter. Now, since I divided by 1,000 to get this, if I didn't divide, I would have gotten 9,000 here. So that at the end of the day, we divide. If you divide 9,000 by 1,000, you get 9 meters. Now, let us take another question. Now, we have this third question, of course, the last question for the day. A wire of 5 ohm resistance is drawn out so that its new length is 2 times the original length. If the resistivity of the wire remains the same and the cross-sectional area is halved, this is the condition. This one remains the same. The resistivity is the same. Now the cross-sectional area is halved, of course, divided by 2. The new resistance is dash. Now, solution. The new resistance must be either 40, 25, or 10 ohms. So we have there are 2 different here. We have the original wire here, and we have the new wire. We have the new wire here. Now we map out all these. Well, in terms of resistance, what is it? I said a wire of resistance 5 ohms is drawn out so that its new length. Now the resistance now has here R here is 5 ohms. Now under the new one, we are looking for the new resistance now, so that its new length is times 2 of the original length. That means in terms of length here, L here is the first one is L1. Now here, this one L1 here will give us here 2L for this one. Remember, they say 2 times the original. This new length is times 2 of the original. Okay. Then in terms of resistivity, they say the resistivity remains the same. Resistivity. The resistivity rho for this one is rho here and rho here the same. All the rows are the same here. Okay. Area now. Area. The new one, resistance of this, and the cross-sectional area is out. Now, the area now, let's say area here is A1. Now, A1 here is A over 2. It has been reduced now. Check the rate at which it's going. L here is L1. Here it is double. Now, A here, the area of the new one is reduced. Now, what do we have here? I think we are done with this. Now, what do we do? Solution. We say, but resistivity rho is equal to RA all over L here. RA all over L. Which will give us, for this one, is equal to RA all over L here. So what do we do here? Now we have here, let's say R1 here, and then this one is R1. L1 here is L here, please. L1 here is L. Now this one we can call here L2, which is the second length. Here is the second resistance. Now resistivity here, we can say resistivity 1 here. This one is resistivity 2. A1 here is A, while A2 here is A over 2. Now what do we do? This one is for the first one. For the first one here, we can have the R1, A1, L1. We can have here as R2, A2, all over. Here will give us L2. What do we do at this point? At this point, we equate the two. We equate the two. When we equate the two, we now have that this one is equal to this. So, which will now give us, when we equate the two, we have, please permit me to write here before I clean. R1, A1, all over L1 is equal to R2, A2, all over L2. At this point, you can cross multiply at this point now. If you cross multiply, we have R2, A2, L1 is equal to, we multiply this side, R1, A1, L2. Okay. If we at this point now, we are looking for, we are looking for R2. So make R2, since R2 is what we're looking for, make it the subject. If we make it the subject, R2 will now give us R1, A1, L2, all over A2, L1. At this point, now this is the formula to use at this point. Permit me to clean the board so that we can substitute all these values there. Now, if we substitute those values, we are going to have, I'll start here and then later on clean this one. So R2 is equal to, in place of R1, I'll have 5. 5 times A1. A1 is A multiplied by L2. L2 is 2L. 2L all over A2. A2 is this side. A2 is A over 2. A over 2 multiplied by L1. L1 is L from here. So I can now clean this, because I have substituted all these values so that we can have enough space to write. So Having substituted that, we can now have here. If we have, since we have R2 is equal to 5 times A times 2L all over A2 multiplied by L. What do we do here? In this case, we rationalize this. If we this is an improper fraction, so we rationalize it. If we rationalize it, we now have that R2 is equal to 5 times A times 2L all over A times L multiply, this one will now come up, multiply by 2 over 1. So which will now give us 5 times A, at this point, A can cancel A from here, L can cancel L from here. So we now have 5 times 2 times 2, which will give us that R2 is equal to 5 times 2, 10. 10 times 2, 20 ohms. Therefore, the resistance of the new wire will now give us 20 ohm, and of course it is option B. Okay, this is where we draw the lesson to an end. Please, if you have not subscribed to this channel, don't forget, give it a like and then subscribe it, send it to your friends, because that is what motivates me to continue to create more content for you. For more detail on this, for more examples, please, there is a link in the description button below. Click that link and join our larger class so that we can have online interaction. Thank you very much. See you in my next video. Thank you.